Well, once again, hello. Let me talk to you a little bit about what we did on Thursday, and that was we spent a little bit of time talking about how we came up with this model for igneous rocks, and we know now that there's more than one model, and that was an extremely difficult task to do because there were so many variables involved with igneous rocks. You have light colors, dark colors, you have crystal sizes all the way from coarse to fine, and then this particular model uses the Earth's surface and whether or not the rocks were formed underneath the surface or at the surface itself. Then we talked a little bit about that experience of arguing from evidence, where you had to come up and argue for your model. We're going to do a lot more of that as we proceed on into our course in the spring. We're going to move now into taking a look at metamorphic rocks, but in order to do that, I want you to copy down this rock cycle. So pause the recording right now and draw the diagram that you see right here, the model that you see. Just get that in your notebooks. Now that you've had a chance to take a look and draw that model, let's see if we can zero in on it a little bit. So we know about igneous rocks. They're up here in the model. And we know that igneous rocks are formed from magma, and that's over here. Whoops, let me see if I can get a better colored pen for you. Here's a blue one. Magma's over here. That means these were completely melted all the way down, and then when it cooled, it formed igneous rock. So that's the only way that igneous rocks are formed, completely melted material all the way down. Now we're going to begin to talk today about metamorphic rocks. Metamorphic rocks are created from heat and pressure. That's why I have heat and pressure over here. So they're not completely melted. They aren't in the totally liquid state. They're in that state that's sort of between being a solid and a liquid. They've been warmed up. They're pressurized, they're under a lot of pressure, and then when they have a chance to cool off, then they become metamorphic rock. Let me give you an example of that. You know what a candle is, and you know that when you light a candle, it melts. But have you ever played with a candle that has not been lighted, just the candle itself, and you just held it in your hand and you kind of just rubbed it around, rub that wax around a little bit? You probably, if you've ever gone to a Christmas Eve candlelight service and you're sitting there in the sermon and you've got this candle and you're so excited to light it, you know, you're holding it, you're rubbing it in your hands, and after a while it gets soft and you can start to bend it a little bit, you can push on it. That's the idea behind the heat and the pressure that is used to form a metamorphic rock. So let's take a look at another model of that. So on the left-hand side over here, we have a model that shows the Earth's surface right here. And you can imagine if you are a rock right down in this area, underneath the Earth's surface, that you are being affected upon by the molten rock down below. The heat is rising and it's kind of warming you up a little bit, but you're also receiving pressure from the weight of the other rock on top of you. So if you're this guy right here, you're under both heat and pressure. So that's a model of what that looks like in the Earth's surface, and the way this plays out on the real Earth is that once that material has had a chance to be heated and pressurized, and then the heat and the pressure go away, and now it's had a chance to cool off, then if that gets eroded away or somehow brought back to the Earth's surface, we end up with rock that looks like this down here. And you can see some of the layers that we had in this model right here still exist, but they've been folded, they've been moved around, they've been pushed, they've been molded into a different shape, just like that candle at the Christmas Eve service that you've been playing with a little bit. So you can imagine that that's what's happening with metamorphic rock. Since this happened over a large region, we call that regional metamorphosis. Imagine what would happen, let me go back to this diagram on the left. Imagine what would happen if you're a rock right in through this area where that hot material is not quite touching you, but you're getting an awful lot of heat and pressure from that. from the contact of this hot material here and the pressure from above, that's called contact metamorphism. So there's several ways to describe the metamorphic processes that take place. So what you're going to be doing in class this week, remember, I will be gone. I'll be in Washington, D.C. But what you are going to do is I'm actually going to give you a model that will allow you to identify metamorphic rocks. And so given that piece of paper, that key, you'll be able to take a look at the texture of the rocks, the grain size of the rocks, the composition, in other words, what minerals make them up. Remember what? This is why we spent so much time on minerals, because you're going to see these again and again and again. And then the type of metamorphism may be another characteristic. And then there'll be some description, comments that help you figure that out. And then eventually you'll come up with the name of the rock. So just like we did with minerals, you'll be given a rock, sample number 1, sample number 2, sample number 3, and 4. And what your job then to do is to take a look at each of those samples, match them up with the key that you'll be given, and then in your notebooks write down number 1, what the name of it is, number 2, what the name of that one is, 3 and 4, and then you'll have a list of metamorphic rocks that you've identified. And then in next week's podcast, I will see how far you've gotten with identifying those metamorphic rocks, and then if you've gotten far enough, I will give you the answers to those, and then we'll move on to the next type of rock the following week. So have a good week, and see you soon.